Alright, so there are a couple bullet points from the study guide related to this week's exam, exam 6. So we just wanted to cover these bullet points and try to help clarify aspects of them for you all. So this first one is about potential energy. So you want to have a strong idea of what that means. So potential energy is the potential for the position of particles to change due to attractions or repulsions. Right, so if I have particles that attract in general far apart from one another versus close together, well, if they're already close together, what potential do they have to move their position? Not much. If they're far apart, there's a potential for their attractions to pull them together. So this would be a higher potential energy, and this would be a lower potential energy. Likewise, if the particles are the same charge and they're close together, well, there's the potential for their attractions to push them apart. So that's a higher potential energy versus if they are far enough apart where their repulsions aren't likely to push them much further. So we want to make sure we understand that a higher potential energy state, because there's a potential for change, is unstable. It's a state where the particles are not going to stay in their current positions because their attractions or repulsions are going to push them to different positions. So let's address the actual question here. Now that we've got that basic stuff hopefully making sense. So if I have some bonds between atoms and I break them, the amount of energy required to do that is going to depend on how strong the bonds are. Right? So a bond isn't much different from what we just said. A bond is nuclei sharing electrons, and the electrons in the electron cloud, if it's a sigma bond especially, are going to be right between the nuclei because that's where the constructive interference occurs for the bonding molecular orbital. And the negatively charged electrons really exist all over the whole cloud, but their most probable location is where the constructive interference is, so they attract nicely to the positives. So when I have a bond, even if it's a weak bond, the attractions are nice, everything's held close together, there isn't much potential for anything to happen. If that bond breaks and I'm looking at the potential energy change, meaning that the nuclei get further apart, because the electrons have to now an individual atomic orbital, they can't attract to both nuclei, this is less stable. I've effectively broken some of the attractions by pulling an electron away from one nucleus and only allowing it to be around one nucleus at a time. So I'm going from a low potential energy to a high potential energy. So we know anytime bonds break, that's always going to be absorbing energy, because energy can't be created out of nothing. If I'm starting at a low potential energy and I have a higher potential energy, that potential energy input has to come from the surroundings and be absorbed into the system. So if that bond is relatively weak, that means that the attractions aren't really that good to begin with. So I still have to put energy in to break the bond. So actually probably a better example of this would be looking at a pi bond. So let's say instead of looking at a sigma bond here, I have to break a pi bond. So I've got my sigma bond is already forming. We'll just not draw that in if we're just focusing on the pi bond. If there's a pi bond, the electrons exist above and below the plane, right? That's where the p orbitals are side by side overlapping. So the electrons and the protons are still arranged in a way where they can attract pretty well. So if I break that bond, maybe by rotating the carbons, so that maybe one p orbital is no longer in the same plane as the other, there's no overlap, the pi bond is broken. So now instead of the electrons existing in the area of constructive interference close to the nuclei, they're now in their own individual atomic orbitals. So that's not a very strong bond to begin with, because the electrons are not that close to the nuclei. If I were looking at a sigma bond, the electrons would be closer to the nuclei. So sigma bond has a greater amount of energy difference between its initial low energy and its higher energy state where the bond is broken. So if I have to break a weaker bond, since it wasn't that stable to begin with, here there's already some potential energy, because there's a potential, if these electrons aren't that close to the nuclei, for them to get attracted to other nuclei, or for them to move closer. If there were space, an empty space, and there wasn't already electrons in there repelling, they have the potential to get closer. So there's a little bit more potential energy in a weaker bond or a weaker attraction or an arrangement of electrons that doesn't put them that close to the nuclei. So if that already starts relatively higher in potential energy, and I'm going to make it go to an even higher, so we'll just call this high potential energy, an even higher potential energy, that requires me to increase the potential energy, absorb energy from the surroundings. So then let's say we're going to make these pi bonds into sigma bonds. So some new atom comes in with an orbital that it's going to overlap head on with the orbital here, and a new atom comes in here with an orbital, it's going to line up and overlap head on there. That would create some new sigma bonds, right? So those two atoms would then share electrons right between the nuclei, and these two atoms here would, whatever they are, would share electrons mostly between the nuclei. So I have to put some energy in to break a weak bond, but then when a new stronger bond is formed, that's lower in potential energy because there's less potential for change when the electrons are held right between the nuclei in a very stable molecular orbital where the overlap occurs between the nuclei and they can form more attractions there. That's going to be lower in potential energy than either of these situations. So that's like where I've got a relatively high potential energy to begin with. I have to put some energy in to break the bond, but then when the new bonds form, they're the most stable of those three possible states. And so when the new bonds form, that's the lowest potential energy of those options. And so that's where I get a value for delta H that is negative overall. So how does that affect the temperature of the surrounding? Well, if the system is releasing energy into the surroundings potential energy, or not potential energy, but heat is increasing. So this is potential energy that the system loses, but it's kinetic energy that the surroundings absorb or increase. And so that gives you a temperature increase. There's an increase in temperature because the surroundings are absorbing the energy that the system released. And so in the second bullet point here, we're talking about breaking stronger bonds and replacing them with weaker bonds. So that would be the opposite. If the bonds are already holding the electrons in orbitals that allow them to form nice attraction, there's not much potential for them to rearrange and attract in any better way than they already are, then that's a low potential energy state. There isn't potential for much change. The only way I can get change to occur is by adding energy, right? So when we think of potential energy, we're thinking of how much potential is there for this to undergo a change without adding any energy. And there's very little potential energy in a sigma bond, especially compared to a pi bond. So this would start off at a low energy. I would have to put a lot of energy to break these stronger attractions, and then to create this higher energy state. And then if the new bond forms, but it's not that strong because the electrons can't get that close to the nuclei, it's still relatively high in potential energy compared to the initial state. And so that would be a situation where for the system, I've got to put energy in. To get from here up to here, I've got to put energy in, and then some energy is released, but not as much as I put in. So on net, I'm putting in a positive quantity of energy. And so that energy has to come from the surroundings. And so the surroundings would go down in energy. And that would cause a temperature decrease. Because in the surroundings, it's generally kinetic energy, and the system, because of bonds breaking and forming and creating different stability or potential for the electrons, it's usually a potential energy change that occurs for the system. Any questions about that? Alrighty. So this other question was requested that we discuss, and this is a great example to talk about delta G with. So if you're given a situation like this, and you have some given information about the heat change for the reaction or process or system, if it's endothermic, it's absorbing heat. So there's a net increase in the potential energy or heat energy that the system stores. If there's an increase in entropy, I know delta S is positive. So to answer a question like this, if I want to get the sign delta G, and I have information that allows me to determine the sign for delta H and delta S, then I want to be looking at this formula. So you can write it like this, which is how we normally would write it in Gen Chem 2. Our textbook prefers to think of it as adding two quantities. So a minus T delta S is the same as adding a negative T delta S. So we think about adding these two terms together. If they're both positive, I'll end up with a positive delta G. If they're both negative, adding two negatives will give me a negative delta G. If one is positive and the other is negative, then the temperature will determine which one dominates and determines the sign for delta G. So let's take a look at these situations. We've got a positive for delta H, and we've got a positive for delta S. But we've got a negative sign here. So a negative temperature, and the temperature is always going to be in Kelvin. So the temperature I plug in is going to be positive, but there's a negative sign in my formula. So I've got two positive numbers multiplied by a negative sign. That's going to make this whole thing negative. So what will the sign be for delta G? Well, it'll depend on which of these values is bigger. Is the positive delta H bigger, or is the negative value for T delta S bigger? I don't know. It depends on the specific numbers, obviously. So in this case, I end up with the sign for delta G being dependent on the temperature. Because temperature is included in the formula, if I increase the temperature, I'm going to be increasing this value that I get when I multiply this stuff together and apply the negative sign to it. And if I increase that more and more and more by continuing to increase temperature, eventually at some point it will be larger than the other value, and I'll get a negative delta G at high temps. If the temperature goes down to much smaller values and I continue to decrease it, this term will get smaller. Eventually it will become smaller than the positive term, and so when I add them, I'll get a positive value for delta G. And the value in knowing this is, we know a negative delta G means the process is spontaneous. It produces mostly products. So this is a situation where I want to increase the temperature to make the equilibrium shift toward the products and produce more products than it would shift to produce at a lower temperature. If it's exothermic and delta H is negative, and there's an increased entropy, so delta S is positive, those are the conditions that will always lead to a negative value for delta G. Because if I put a negative in for delta H and a positive in for delta S, a negative times a positive is going to give me a negative. So in that case, I'm adding two negative values, and so delta G is going to be negative for sure. So there's no way in that case to change the temperature to make delta G positive, and this will always be a product favored situation no matter what temperature I use. Conversely, if I have an endothermic reaction where delta H is positive and there's a decrease in entropy, so delta S is negative, well, that's a situation where delta G is going to be positive no matter what I do, because the positive value for delta H is added to a negative times a negative for delta S. If delta S is negative, I plug a negative in here, I've got a negative times a negative, that's a positive. So that means I'm adding two positive values, and so that's going to give me a delta G that's positive no matter what I do. Even if I change the temperature, I can't make that process product favored or give me more products than reactants when it reaches equilibrium. And so then the last scenario here, exothermic, delta H is negative, but there's a decrease in entropy for the system, so delta S is negative. So if delta H is negative and I add to that a value for delta S that's negative, negative times a negative gives me a positive. So this is similar to what we had over here, where it depends on temperature, but the situation is reversed. In this case, since my T delta S term is positive due to the two negatives multiplying together, if I have a positive here and I increase the temperature, what's going to happen? And this positive number is going to become larger than the negative. And so that's going to give me a positive value for delta G, or a process that favors the reactants at higher temperatures. So sometimes the temperature doesn't really matter in scenarios B and C. Sometimes the temperature will make the process more spontaneous. But that will only be the case where delta S is positive. If delta S is negative, and I'm plugging a negative in here, negative times a negative is positive. So the T delta S term will always be positive when delta S is negative, and if I increase the temperature, I'm only going to make that a larger and larger positive value, and delta G will become more positive. And so in that situation, it becomes non-spontaneous or reactant favored at higher temperatures. Any questions about that? Alright, so here's our continuation with Chapter 6. From last week, we were talking about a lot of these thermodynamic concepts, and we're going to continue to employ them whenever they help us understand reactions. And we're working toward looking at some simple reactions where bonds break and form, try to understand the energy involved, the entropy involved, predict whether we're mostly going to get products or reactants. And we want to understand the nature of these reactions, what are the steps involved, how do the electrons move, how can we control these reactions and make them more effective at giving us the products we want to make and shift them in the direction we want, how can we control the kinetics and make sure it happens at a reasonable rate. So there's a lot going on here. There's a lot we have to consider at once. But the next thing we're going to talk about is the main ways in which molecules react. And one of those involves nucleophiles attacking electrophiles. Right, so when we think about these two terms, hopefully you've thought about these already to answer the quiz questions, but a nucleophile in general has to have a pair of electrons that it's going to share with the electrophile. The nucleophile is exactly the same as a Lewis base. base do? It shares its lone pair. If it's a Bronsted base, it shares it with a proton. If it's a Lewis base, it shares it with anything. And so the acid has to be something that can accept the electrons. So we're not talking about transfer of electrons. We're talking about sharing electrons. So really, when a nucleophile or a base attacks an electrophile or an acid, what's happening is simply a new bond is forming between them. And so that's the simplest example where a new bond would form between the nucleophile and the electrophile. So we have to learn how to identify nucleophiles and how to identify electrophiles. That's what we're going to focus on today, and some of the main ways that they react, and then we're going to expand and look at a lot of specific reactions starting next week. So these types of reactions follow some key patterns. We're going to try to learn those patterns and then emphasize them with a lot of practice. So let's take a look at these compounds here. What do we see? Well, when carbon bonds with something like chlorine, that's not too unfamiliar to you, hopefully. The chlorine is more electronegative than carbon by half an electronegativity unit. So the shared electron pair, or the cloud that's shared over these atoms, gets pulled away. That makes the carbon a partial positive. So that makes this site a little bit electrophilic. It makes it so that a nucleophile, in general, some atom that might have electrons to share, can come in and start sharing them. You might be thinking, well, how can that be? If the carbon already has 4 bonds, it can't accept in and share another pair of electrons, because that would create this structure here, where the nucleophile now has a bond to the carbon. That's what this arrow is indicating, an attack of the nucleophile on the electrophile. That can't work if I'm creating 5 bonds. So this is an electrophilic site, but only because, not just because of the electronegativity difference that creates a positive to attract the negative charge of the electrons of the nucleophile, but also because the chlorine can actually take these electrons and leave with them. We call that a leaving group. So we're going to see a lot more examples of this as we move forward. But you got to be careful with these. Don't form any 5 bonded carbons. If you're going to have a nucleophile attack a carbon, it either can only already have 3 bonds, so when the new one makes the 4th, or there has to be one group, atom or grouping of atoms that can leave with a pair of electrons so that the new one becomes a replacement for the old one. So one thing we look for, though, is electronegativity differences. So when you see atoms bonded to carbon, you want to look for their electronegativity difference to try to determine whether there's any charge there on the carbon. If it carries a positive, it may be electrophilic. If there's the ability for it to form a new bond, maybe an old bond has to break in order for that to happen. Alternatively, the carbon could take a negative charge. So this doesn't happen very often, but if the carbon's bonded to an atom with a lower electronegativity than it, I think lithium's electronegativity is around 1, I don't know exactly, I think it's around 1.0. Carbon's obviously 2.5. So there's a big electronegativity difference there. And these electrons are mostly on the carbon. And if we think about that bond between the lithium and the carbon, or really any bond between carbon and a group 1A or 2A metal, it doesn't have to be lithium, those group 1A or 2A metals do not effectively share electrons. They don't have any lone pairs. If we look at lithium, what does it need to do? Or if this were magnesium, like the quiz question, what does it need to do? It needs to leave the electrons behind. It needs to escape and not have those electrons around at all so that it can make a noble gas configuration. Right? These are elements that don't have a tendency to pick up electrons in the outer energy level, because that's not going to make a noble gas configuration. They lose those electrons to become a +1 or a +2. So this is a situation where this shared pair is really weakly shared. The electronegativity difference allows me to see the negative side and the positive side, but beyond that, thinking about the noble gas configuration allows me to see that this carbon really, for the most part, owns these electrons, and they're pretty much existing almost exclusively on the carbon because the lithium or magnesium is not effective at sharing those electrons because it breaks up their noble gas configuration. So to make their noble gas configuration, these electrons are primarily owned by the carbon. And what that does is it makes the carbon, specifically, a great nucleophile. It's a nucleophile because it has a pair of electrons that it's getting ready to share with something else. So if I put these two atoms together, or these two molecules together, what would happen? The carbon would use this pair of electrons. It would start sharing them with this other carbon, and that would push out the chlorine. What would be produced? The lithium would be more stable on its own, so it can make a noble gas configuration. The chlorine is perfectly stable with a full octet and a full negative charge. Very little charge imbalance there. Larger atoms are good at stabilizing a negative. And this new bond would form between the carbon and the other carbon. One carbon was the nucleophile, the other carbon was the electrophile. And so this is a bit of a sneak preview at one of the ways that chemists use to make new carbon-carbon bonds and build up piece by piece complex structures involving carbon that might be useful molecules like pharmaceuticals and other fine chemicals. So I'm just trying to getting an introduction to that there. Any questions about that so far? So when we're looking for nucleophiles, what do we look for? We look for a negative charge. We're looking for a formal negative or a partial negative, because what a nucleophile is going to do is take a pair of electrons and start sharing them with something. If it were positive, then it would hold those electrons in. It wouldn't want to share them. If it started to share them with another atom, it would take on a +2. That's not going to be stable. So a nucleophile typically has either at least a partial negative or a formal negative. That way, it'll be driven to start sharing those electrons with something to balance that charge out. And so we saw the carbon here. These electrons, being mostly on the carbon, almost act like a lone pair on the carbon, giving it almost a full negative, which for carbon would be very unstable. And so that very large partial negative on that carbon means, since the lithium is stable on its own, it would go away. The carbon can use those electrons to attack an electrophile, forming a new bond there between carbon and an element that can actually effectively share those electrons. An oxygen with a negative is a great nucleophile because of the formal charge. Oxygen, if it had two bonds and two lone pairs, would be neutral. That would be much more stable, so it can start sharing those electrons with an electrophile as well to form another bond there and balance out the charge. A neutral oxygen, so these two are both quite strong because of the amount of negative and their tendency to start sharing to avoid forming an unstable negative. These two are much weaker. They're still slightly nucleophilic because the oxygen does still have lone pairs, and it is more electronegative than carbon and hydrogen, so it is carrying a partial negative. So it could start sharing one of those lone pairs with an electrophile. That would give it a positive charge, and that would make it unstable, so it's not a great nucleophile, but it does have the possibility to act as a nucleophile if the electrophile is unstable enough, right? So if I think about what's a really unstable electrophile, well, the classic example of a really unstable electrophile would be a carbocation. Why is a carbocation a great electrophile? It needs electrons, right? The prefix phile means love. It philes or loves electrons because it only has 3 bonds and it needs a 4th bond to make its noble gas configuration and balance its charge. So this oxygen would very easily come in there and start sharing electrons. And what would that form? Well, the oxygen would still be bonded to everything it was bonded to, but one of those pairs of electrons would now be shared with that carbon. And that would create a positive for the oxygen. So I would still have a net positive, but at least now my atoms all have noble gas configurations versus this carbocation which didn't. So that would help that reaction to go forward. Even a pi bond can be thought of as a nucleophile, because a pi bond can start sharing its electrons as well with a new atom. Those pi bonds, as we said, aren't held that closely to the nuclei, and they have a little bit of potential energy, a potential to react. So if they started to be shared with some nucleus in a sigma bond, that might be more stable for them than as a pi bond. So if those two were to react, what would that give? Well, these 4 carbons would still be there in a zigzag. And this pair of electrons, instead of shared between them as a pi bond, it would maybe form a head-on overlap with this carbon to add that carbon in there. And as the electrons get pulled away from this carbon, which only has 1 hydrogen, it would create a carbocation there. So it'd still be unstable, but it wouldn't be as unstable. And if this is the only available pair of electrons, because it's the only slightly unstable pair of electrons, it would be the one to act as a nucleophile and attack the electrophile to share electrons with it. So as we said, electrophiles can attract electrons, and so they are typically positively charged. So as we showed earlier, a good electrophile either has 3 bonds, or it doesn't have to have 3 bonds, but some number of bonds that leaves it deficient in electrons where it could take on another pair. So a nucleophile and just some general nucleophile could come in here and form a 4th bond to that carbon. That would really help to stabilize that carbon, completing its noble gas configuration, avoiding a positive charge. So carbocations are really great Lewis acids or electrophiles. They mean the exact same thing. We also said a partial positive on a carbon can work, but not every time. So this partial positive on this carbon is only going to be an electrophilic site. It's only going to attract a nucleophile in, because I can't form 5 bonds, if there's another grouping of atoms that can leave, called a leaving group. So in this case, I've got that. The chlorine can stabilize a negative charge if it leaves on its own, so that allows the nucleophile to come in and push it out. If I had something else, instead of a chlorine here, maybe I had hydrogen, or maybe even like nitrogen. The nitrogen's more electronegative than carbon, so the electronegativity difference here would pull electrons over. It would create a partial positive on this carbon, but this carbon is not very electrophilic, because to be an electrophile, the nucleophile has to be able to attack and either make a 4th bond, but there's already 4 bonds here, so the only option in this case, since there are 2 hydrogens here, would be to push out this nitrogen as a leaving group. But if nitrogen leaves with those electrons that it was sharing, and it pulls them on and becomes a lone pair, it's going to form a negative. And since it's a small atom creating a fairly large charge imbalance, and we know from our acid-base experience that a negative on a nitrogen is not very stable. It's less stable than a negative on an oxygen, which is also a small atom and not very stable. But a chlorine or a bromine, a larger atom that can carry and stabilize a negative charge more effectively, acts as a much better leaving group and allows the carbon it's attached to be a better electrophile, more likely for a nucleophile to attack there and push the chlorine out than for the nucleophile to attack over here and push a nitrogen out. Well, we see a lot of reactions as we move forward to help clarify that in your mind. So here's an example. I want to label the electrophilic and nucleophilic sites. So first thing we want to do is to put in the lone pairs where they belong. So where are our electrophilic sites? So most of the time when students answer questions like these, they're pretty good at noticing the sites for the heteroatoms, the nitrogens and oxygens. But a lot of these carbons are reactive as well in one way or another. So we want to make sure we can be as thorough as possible. So over here, this oxygen pulling electrons toward it from the carbon, creating a partial negative on it. That makes this oxygen's lone pair a weak nucleophile or a weak nucleophilic site. The lone pair could be shared with something, this extra negative on the oxygen would allow that lone pair to possibly start to be shared with some electrophile. Same thing here. This one will also be weak. I'll just put WN for weak nucleophile, weak nucleophilic site. The nitrogen is a little bit stronger, so I'll just put nucleophile there instead of weak nucleophile. Why is the lone pair on the nitrogen better than the lone pair on the oxygen for acting as a nucleophile? Well, if the nitrogen were to start sharing its electron pair with some electrophile, then the nitrogen would end up with a positive charge. If the oxygen were to do that, then the oxygen would end up with a positive charge. And as we've been saying throughout the acid-base section, when nitrogen picks up a positive charge, because it's not as electronegative as oxygen, it doesn't rip the electrons back as much. But this oxygen with the positive is pretty unstable because it's so electronegative with the extra proton in its nucleus compared to the nitrogen. It's going to start pulling these electrons away more, and that makes it less likely to act as a nucleophile and start sharing them if it's just going to end up ripping them right back again. So that's why the oxygen is a weaker nucleophile than the nitrogen. This lone pair is not really nucleophilic. It's not going to end up being shared with something to create a +2 on the oxygen. Here, this negative is a pretty decent nucleophile. This is stronger. I'll put SN there for stronger nucleophile. Since it's fully negative, since it has a full negative charge, if it were to share a pair of electrons with an electrophile and make a new bond, it would be neutral. That would actually be great for it. So that's very likely to happen at that site. There's one carbon in the structure that's nucleophilic. So just take a second, see if you can think about what carbon that might be, and then I'll show it. Which carbon in the structure is the most nucleophilic? It would be this one right here. How is that carbon nucleophilic? Well, it's got 4 bonds already. It doesn't have a lone pair, but it does have resonance with the lone pair of the oxygen. Because this pair of electrons can shift in here, it's an allylic lone pair, and shift these onto the carbon. That means this oxygen isn't actually carrying a full negative, it's actually shared between both the carbon and the oxygen. So the alternative resonance contributor for that part of the structure, which would look like this, does put some negative and some of that lone pair characteristic on the carbon. And so this carbon is actually a very strong nucleophilic site, even more so than the oxygen. It'd be very likely to start being shared with something to stabilize that negative charge if there were anything around that could accept and share that pair of electrons to form a new covalent bond. Any questions about the nucleophilic sites there? Alright, let's look at the electrophilic sites. The electrophilic sites are generally sites that carry a positive or have a incomplete noble gas configuration, so more electrons can be shared with them. So the most electrophilic site here is a carbon, and it is right here. Why is this site so electrophilic? There's resonance. Right, so we talked about resonance earlier in the semester. I warned you it was going to be a topic that keeps coming up. So due to the fact that these pi electrons are very easily pulled up here, especially because the oxygen's positive, the same thing can happen here, but since the oxygen's neutral, it doesn't pull the electrons as much. There's a very significant resonance contributor where if these electrons shift up, I'm just looking at that part of the structure, if they shift up to the oxygen, it'll leave a carbocation at that site. So even though this carbon right now has 4 bonds shown, it has significant carbocation character. It's a strong electrophilic site because any nucleophile that's around can come in here and attack and form a new bond and push those electrons up to the oxygen. So a 4th bond can occur to that carbon, alleviating the positive charge there and alleviating the positive charge on the oxygen at the same time. So that's a nice strong nucleophilic site here. I'm sorry, electrophilic site there. This one is also electrophilic, but it's weaker, so I'll just put E for electrophilic site here. Same thing, the nucleophile could attack here and push electrons up, but that will create a negative on the oxygen, whereas over here it just makes the oxygen neutral. So it's not as likely to accept a new pair of electrons if it creates any instability associated with the formal charge that would form on that oxygen. And those are really the only two electrophilic sites we have here. You might consider this carbon here to be slightly electrophilic because the oxygen is pulling electrons away due to being more electronegative than the carbon. That does create a little bit of a partial positive here. But to be electrophilic, the nucleophile has to be able to attack and form a new bond. And the only way that can happen if there are already 4 bonds on a carbon is if one atom leaves with the electrons. But if the oxygen pulls these away to make room for the new bond to come in, it's going to create a full formal negative on the oxygen, which is pretty unstable. So we could call this a weakly electrophilic site, but especially if it's on a structure with other sites that are more electrophilic, it's not going to be a reactive site. Typically, we would only react one site on a molecule at a time. So ultimately, here, where if I did take this structure and react it with an electrophile, it would be this carbon would be the most nucleophilic site. That would be the first most likely site to attack the electrophile. If I reacted it with the nucleophile that already had electrons, they would come in, and this would be the most electrophilic site because it would attract the new electrons in and stabilize the positive charge. Here was the quiz question. You can identify the bromine as nucleophilic. It has a full negative. It can start sharing those electrons with some electrophile. The magnesium is neither. The magnesium needs to make a noble gas configuration. So the electrons it's sharing here with this carbon, as we said earlier, the magnesium does not effectively attract those electrons. It needs to be off on its own so it can make a +2 charge and leave these electrons behind on the carbon, which means that the carbon is a very nucleophilic site. The carbon is a nucleophilic site because it can pull these electrons away from the magnesium very easily, and that would make too much negative on that carbon, and so it would start sharing those electrons with an electrophile to form a new bond between the carbon and the electrophile. On this structure over here, I've got an electrophilic site here with a partial positive. A nucleophile can come in and push the chlorine out to avoid a 5-bonded carbon. My most nucleophilic site is right here on the nitrogen's lone pair. As we said before, since nitrogen isn't super electronegative, it's relatively willing to start sharing its lone pair with something that's positive. It's already carrying a partial negative, and so there's a natural attraction there as well in that sharing. If this electrophile is really unstable and it needs electrons badly, the nitrogen would be more willing to share them than either the oxygen or the chlorine. And so that's the most nucleophilic site there. You could say this one might be weakly nucleophilic, and the lone pair on the chlorine isn't really very nucleophilic. If the lone pair on the chlorine were to start sharing with something, it would just end up being pulled back to balance out the charge on the chlorine. Alright, so now that we have the basic ability to identify nucleophiles and electrophiles, that ability can now be applied to some reactions, and we're going to look at 4 main types of reactions. These 4 patterns can be used to explain a very large number of reactions. So most of the reactions we see this semester from here on out are going to involve one or more of these 4 patterns. The third one we've already talked about. We're going to talk about it more in detail, but any Bronsted acid or base reaction is also a proton transfer, right? We said the acid and the base uses a pair of electrons to pick up a proton, and these electrons stay behind on the acid. We covered this arrow these curved arrows because they are the way that organic chemists communicate about electron movement. So we want to make sure we can represent any new bond forming with an arrow and any old bond breaking. So any proton transfer always has two steps, or two arrows. It's one step, but two arrows are involved. So we're going to talk about nucleophilic attack, loss of a leaving group, carbocation rearrangements, and we're going to use the curved arrows to communicate about them and show how the electrons move in a variety of reactions. So now that we know what nucleophiles and electrophiles are, we can talk about a nucleophilic attack, which sounds exciting but isn't. The nucleophile always starts with a pair of electrons. It could be a lone pair. It could be a pi electron pair. Most of the time it'll be a lone pair, and so the nucleophile will have some degree of negative, and that will naturally allow it to attract a site with positive. And if that site, like a carbocation, can accept a new pair of electrons in and share them, that makes that a great electrophile. So a nucleophile should attack an electrophile, and when it attacks, it will make a new bond. A nucleophilic attack pretty much always forms a new sigma bond. And the way we work with arrows is the same as what we've been doing so far. The arrow starts on a pair of electrons and ends at the location those electrons are moving to. So the arrow could be interpreted as suggesting that the lone pair is simply moving to the carbon. If I think about the lone pair moving to the carbon and existing on the carbon rather than the bromine, and they're not there anymore, I mean, this arrow could imply that. It could imply the electrons are just moving over, but that would create two pretty unstable structures, especially the bromine without a complete noble gas configuration and the carbon with a full negative, creating a large charge imbalance. So we have to use some of our experience with chemistry and formal charges and stability to recognize that this is not a stable outcome, and that this, even though this arrow is showing these electrons moving over here, it's implied that they're not actually being transferred, but they're being shared, because by sharing them, we end up with a much more stable structure that doesn't have any formal charge or incomplete noble gas configuration. So when you see a nucleophilic attack, the arrow is indicating that those electrons are going to end up shared between the atoms. Here's a nucleophilic attack. It's a little bit different, so there are a few variations on this pattern. Here I've got a carbon. It has 4 bonds already, so if the nucleophile is going to come in and make a new bond, like we just saw in the last example, there's got to be something else that's happening. And since we know pi electrons are not shared very tightly between nuclei, pi bonds are susceptible to breaking fairly readily. So if I have a nucleophilic attack on a carbon that's involved in a pi bond, I expect the pi electrons to move away. And in this case, since there's an oxygen that naturally attracts them due to its electronegativity anyway, making a new bond here and breaking the old one so that those electrons become a lone pair is the most likely outcome of this nucleophilic attack. So we use an arrow starting again on the electrons, pointing toward the atom those electrons are going to be shared with for the nucleophilic attack. But we need the second arrow to avoid the implication of an unstable 5-bonded carbon. So the second arrow shows the pi electrons moving up to become a lone pair so that this carbon doesn't end up with more than 4 bonds. Notice how the charges can help us with our arrows. Right? We want to make sure we follow the rules and always start an arrow on a lone pair, but if we think about the electronegativity difference between R, which is a carbon group, and oxygen, and between oxygen and hydrogen, this oxygen is going to carry a fair amount of partial negative, and the electronegativity differences here are causing this carbon to carry a fair amount of partial positive. So especially when you're working on these in the beginning, there's a couple things I would recommend. One, show the relevant partial charges. That can really help you see which atoms are going to attract. And even more importantly, draw the hydrogen atoms in the area of the reaction. Where bonds look like they might be breaking or forming, just draw in all the hydrogens in that area. I know on your exams, most of you probably are not going to do this. And many of you will make mistakes because of that. You'll end up making a 5-bonded carbon, or you won't realize a hydrogen is moving from one spot to another. It's much easier to see what's happening if you draw those hydrogens in that area of the reaction. So in this case, there's no hydrogen on that carbon, but if there was, if we didn't draw it, we might not realize it's there, and that would really cause us to make a bad error, most likely. Since the arrows show electron movement, putting in the charges also helps us to see this arrow is not going to go in the opposite direction. Right? The arrows show electron movement. Electrons are not going to go toward a negative. They're always going to go toward a positive where they're attracted. So that's also another helpful hint. All right, so that's nucleophilic attack. We're going to see a lot more examples of that, obviously, moving forward. The next pattern is a loss of a leaving group. Sometimes this happens in conjunction with a nucleophilic attack. Sometimes it happens on its own. As long as there's enough energy and the collision is strong enough, sometimes these bonds can break. And so if I have one atom that's more electronegative than another, bromine's slightly more electronegative than carbon, it's already kind of pulling the electrons. If that molecule undergoes a strong collision, the electrons can both move on to the more electronegative atom. So the leaving group itself always leaves with a pair of electrons. Always. That is its definition. If the leaving group leaves the electrons behind, it's not the leaving group. If I have a lithium here, something that's less electronegative than carbon, the lithium can leave, but since it's not taking the electrons with it, it's not a leaving group. In fact, the carbon would take those electrons so that the lithium could make its noble gas configuration. So in that case, I could think of the carbon as being the leaving group. Right? So whichever grouping of atoms or atom takes electrons with it when a covalent bond breaks heterolytically, that's the leaving group. So here I've got an example of a loss of a leaving group. Really, this is the only arrow that's showing the loss of the leaving group. The chlorine is leaving with electrons. The other arrows here are just showing resonance. Right? So if I drew the structure here, after the chlorine leaves, it pulls the electrons away, and that's what makes it a leaving group. In that case, I would initially think about a carbocation creating at that carbon, because there'd only be 3 bonds. So the other arrows here are just showing how that carbocation is being stabilized. So they're not showing this, but this oxygen would also shift a pair of electrons in through resonance. So that would give you even more resonance than what the arrows here are showing. But then this is a allylic carbocation right here. This pi bond right here is allylic to the carbocation, so those electrons could move in. That would make a carbocation up here, so these electrons could move down. And then the electrons from either one of these oxygens could shift in there. So there's lots of resonance to help stabilize that. So if a leaving group can be stable after it leaves, like a Cl- or a Br-, something like that, that's quite stable, it might leave if there's a collision. And especially if the structure it leaves behind without those shared electrons anymore can be stabilized through resonance or something like that, makes it even more likely that the leaving group might leave. So if I have a chlorine bonded to just a single carbon, that chlorine is a great leaving group, but it's not very likely to leave and leave behind a carbon with a positive charge if there's no resonance or hyperconjugation or induction, what we're going to talk about a little later, to stabilize that positive charge. But loss of the leaving group technically does show a leaving group pulling electrons with it and leaving with those electrons. So we talked about proton transfer a lot in chapter 3. Proton is simply a hydrogen's nucleus, so proton transfer is a Bronsted acid-base reaction. The Bronsted base uses a lone pair to pick up a proton. So this is very similar to a nucleophilic attack. That's why a Bronsted base and a Lewis base, which is a nucleophile, have a lot in common. There's a lot of crossover between the properties of a substance that creates a negative charge that allows that lone pair to be readily shared with the proton, and it's very similar to a situation where the lone pair could be readily shared with an electrophile. So bases and nucleophiles have a lot in common. They both share their electrons with something. If it's a Bronsted base or it's a proton transfer step in a mechanism, the pair of electrons is going to pick up a proton. And this is the arrow suits off forget about. In every proton transfer step, you need two arrows. One arrow to show the proton forming its new bond, and one arrow to show the old bond staying behind as a lone pair on the acid, the conjugate base of the acid. So that's pretty straightforward. Sometimes you might see a proton transfer with more arrows. Usually only the first two arrows are necessary, and any additional arrows are just showing resonance or other electron flow to give you the most stable resonance contributor. Right? So in this situation, this proton is slightly acidic. Here's my base. It picks up the proton. These electrons stay behind. But this is not the major resonance contributor for that structure, because carbon with a negative is not as stable as oxygen with a negative. So this arrow and that arrow show how the electrons would shift to get to the major contributor, which is what most of the molecules, well, I shouldn't say most of the molecules, the major contributor, which affects more what the hybrid looks like. So we could show that happening all at once and get directly to the major contributor, or we could just show the proton transfer itself, giving the minor contributor, and then the resonance. It's basically the same thing. So either way, if you want to show this proton transfer, you could use multiple arrows, and you could use a minimum two arrows. Either way would be correct for using the curved arrows to show the electron movement in that particular proton transfer. Alright, so that covers nucleophilic attack, loss of leaving group, and proton transfers. The fourth pattern is carbocation rearrangement. So before we can talk about what the most likely way a carbocation will rearrange is going to be, we have to talk about carbocations a little bit more detail so we can understand why some carbocations are more stable than others. So in general, when I have a carbocation, it's always going to be a carbon with 3 bonds and no lone pair. And so if I ever have a carbon that has a positive formal charge because it only has 3 bonds, it will have an empty p orbital. So this is just a methyl group, so it doesn't have a p orbital. But if my carbocation had an empty p orbital and it were adjacent to, say, like a double bond, where those carbons had p orbitals, if this is a pi bond, then the orbital overlap would allow that carbocation to be stabilized through resonance, right? Some of the electron density of this pi bond can shift in through the orbital overlap into the empty orbital. So we already talked about that. We talked about how allylic carbocations, or carbocation that's allylic to a pi bond, is somewhat stabilized through resonance. And that involved the orbital overlap. Well, that's when you have p orbitals, because resonance occurs when p orbitals overlap side by side, and those orbitals are parallel with one another. Right? This p orbital here and this p orbital here are in the same plane, and all they have to do is get close enough to overlap a little bit side by side. And so that really stabilizes a carbocation. To have it be allylic and engaged in resonance really helps to stabilize it. Well, if you don't have resonance to stabilize a carbocation, there's also something called hyperconjugation, which is not as stabilizing as resonance. So resonance stabilizes a carbocation more than any other factor. But the way hyperconjugation works is similar. What stabilized this carbocation with resonance was the electron density of the neighboring p orbitals overlapping side by side, creating a larger molecular orbital extending over multiple atoms so the electrons could cover all those nuclei and attract to all of them at once. Hyperconjugation is similar, but there are a couple key differences. So let's take a look at the differences. So here's my methyl group. It's a CH3, and here it is right here. So we know that orbitals can eclipse one another, right? Generally, when we're talking about eclipsing, we think about Newman projection, where if the front carbon has something bonded to it, and the back carbon has something bonded to it, and they're in the same plane and they're eclipsing, then we think of their electron clouds repelling. That makes it unstable. In hyperconjugation, it's similar, but because this orbital here is empty, there's nothing in it, it would actually be more stable if it rotated into a position where it could eclipse one of the bonds on the neighboring atoms. So if this is a methyl group, it's really a carbon with some H's here, and there are 3 H's. If this single bond rotates so that any one of these H's gets into the same plane as this empty orbital, I would have eclipsing. But instead of eclipsing between full orbitals that would be unstable due to repulsion, now I'm eclipsing a full orbital and an empty orbital, and so there's 2 electrons in that area of overlap, which is perfect. That's what I want to make it even more stable. So I'm kind of sharing some electron density from a sigma bond into an empty p orbital. So that's one difference. This is a sigma bond. Down here with resonance, it was a pi bond. And when it's a sigma bond, the angle is a little bit different. The pi bonds are at 90 degrees to the plane of the nuclei. And so they're parallel and they overlap fairly readily. If this is a sigma bond here, this angle is 109.5. This is not resonance. This is an sp3 hybridized carbon. Its CH sigma bond is not straight up and down parallel with this p orbital. So the degree to which they overlap is minimal. It's significant, but it's minimal compared to resonance. In resonance, they overlap side by side. In hyperconjugation, they overlap side by side, but the angle of the sigma bond is kind of pointing away a little bit from the pi bond. They're not quite parallel. So there's not as much orbital overlap. And if there's less orbital overlap, there's less constructive interference in the molecular orbital that results from that atomic orbital overlap. It doesn't really put the electron density as much right in the area close to the nuclei. So there's some orbital overlap, and it allows some of the electron density of the sigma bond to shift over here in a molecular orbital that's created from that overlap, and that allows it to stabilize to, close to both nuclei, but not nearly as much as resonance because the overlap is not as effective when the orbitals aren't really side by side and one is kind of pointing away from the other. If the single bond here rotates, any one of these hydrogens could fly up into this plane and overlap with the sigma bond. So it doesn't only stabilize it in this one rotation. It stabilizes it in any rotation where the CH bond eclipses with the empty p orbital. So that's how hyperconjugation works. So we can use that to understand this trend here. If I have a carbocation that's only bonded to hydrogens, there's no hyperconjugation. Right? This carbon with this empty p orbital, it's only bonded to hydrogens. So if there's no carbon, there's no sigma bonds here to overlap. So there wouldn't be any hyperconjugation to stabilize that. So a methyl carbocation is neither stabilized by resonance nor is it stabilized by hyperconjugation. It's really quite unstable. There is some induction because hydrogen's a low electronegativity atom. It can allow the sigma bond here to shift a little bit more toward the positive to help stabilize it somewhat. So that helps. But the resonance would be the main thing, and the hyperconjugation would be the next biggest factor, and the induction is not very significant compared to those other two factors. So once I have one carbon group, so remember R represents a generic carbon group, once I have a single carbon group here, whatever plane this p orbital's in, that carbon can rotate one of its hydrogens or carbon-hydrogen or carbon-carbon sigma bond kind of side by side with that p orbital and overlap there and help to stabilize it. If I do that on one side, it stabilizes it a little bit. If I have that happening so the sigma bond here and here, both of those start to overlap and share electron density, it stabilizes it even more. And if it's so-called tertiary, because the carbon's bonded to 1, 2, 3 carbon groups, tertiary, secondary, and primary tell me how many carbon groups my carbocation is attached to. If the carbocation is attached to 2 carbon groups, there's some electron density from both of those sigma bonds that can shift in there and stabilize the carbocation. If the carbocation is attached to 3 groups, whatever plane that p orbital's in, each of these carbons can rotate a hydrogen into the same plane. And they can all transfer some electron density in there, and that stabilizes the carbocation even more. So the more carbon groups I surround my carbocation with, the more stabilized it will be through hyperconjugation. Hyperconjugation is going to be used throughout the course and next semester to explain a lot of things. So try to keep in mind that phenomenon and practice it a little bit so you don't forget about it. Induction is also important here, but the induction is pretty similar all the way down the line, because whether it's a hydrogen sharing electrons in or a carbon sharing electrons in, and those hydrogens share electrons in, the induction also increases as I add more carbon groups, mainly just because there are more pairs of electrons around. Right? Induction is about electronegativity differences and electrons shifting, just not overlapping with other orbitals, but just the sigma bond just shifts a little bit more toward the carbon, which shifts a little bit more toward that carbon. So the more electrons and bonds I have, the more they can shift a little bit toward the atoms that shift a little bit more toward the carbocation to help stabilize its charge. So because some carbocations are more stable than others, it turns out that when a molecule forms a carbocation, if it's not the most stable carbocation that molecule can exist with, it can intramolecularly rearrange to become more stable. So we're talking about maybe my molecule forms a secondary carbocation, and there's a way for the molecule to rearrange itself quickly to produce a more stable tertiary carbocation. That should happen naturally before a nucleophilic attack occurs. So let's look at an example of that. So let's say I've got this structure here. I've currently got a secondary carbocation. There's only 2 carbon groups to help stabilize it through hyperconjugation. That hyperconjugation, as we said, involves an empty p orbital overlapping with the sigma bond. So if the neighboring sigma bond can overlap a little bit to help stabilize through hyperconjugation, that also means that it can actually shift over. So if these two orbitals are close enough to overlap, then it's definitely close enough for this CH bond to just go over to the next carbon. And that's what a carbocation rearrangement is. It's a situation where either a hydrogen with a pair of electrons, which is called a hydride if it takes the electrons with it, the whole thing will jump over to the neighboring carbon. Or a methyl group can do it. It's got to be a hydrogen or a methyl group that can shift over and end up located on the neighboring carbon. Why would it do that? Because it goes from a secondary carbocation to a tertiary carbocation. And then it stays there because then it can be more stabilized through hyperconjugation, as we described. If there's a nucleophile around, we might expect that nucleophile to attack. For a nucleophile to attack the carbocation, though, there has to be a collision between the two. And these things are bouncing around randomly. Yeah, one is probably at least partially negative, the other is positive, so their attractions pull them together, but they are bouncing around randomly to a degree, so the odds of them colliding right away aren't that high. But since the shift is intramolecular, it doesn't require a specific collision. Any old collision with enough energy can cause this hydrogen to bump over to the next carbon and stabilize the carbocation. So typically, if a carbocation can be stabilized by doing a hydride or a methyl shift to make it go from a slightly less stable carbon to a more stable carbon one carbon over, that will usually happen before a nucleophilic attack because of the intramolecular nature of the shifting of the hydrogen or the methyl group. It's got to be on an adjacent atom. It can't occur too far away. Right? I'm not going to have a hydrogen from here shift all the way over there. There isn't any orbital overlap between this orbital and the empty p orbital, right? So there has to be some orbital overlap for the electrons to shift over, and so that can only occur on the very next carbon over. And we only want to do shifts that make the carbocation more stable. So this one definitely does up here because it goes from secondary to tertiary. So you want to be aware of that. So just want to point out one other thing before we look at this next quiz question. Let's say I had this situation here. Would this carbocation undergo a shift? Well, I want to look for opportunities to stabilize it. There's no way to make it sit on a tertiary center. And after we spend so much time talking about this slide here, students become really focused on the idea of a tertiary carbocation being more stable than a secondary, and that's fine. But you don't want to forget that resonance is more stabilized than hyperconjugation. So a primary carbocation that could be stabilized by resonance would be even more stable than a tertiary or secondary that cannot be stabilized by resonance. So in this example here, I would definitely do a hydride shift because this carbocation is too far away from the double bond. It's not involved in resonance, it's not allylic, but once the hydride shifts over, now the carbocation ends up here, so now it can be stabilized by resonance. So even a secondary carbocation shifting to become a secondary, students might say, well, why would it do that? It's a secondary either way. Well, if it's stabilized by resonance, it's a lot more stable than not being close enough to the pi bond to be stabilized in resonance. So don't forget to look for resonance when you're looking for carbocations and ways to shift them to make them more stable. So in the next quiz question, if I just want you to draw any kind of nucleophilic attack followed by a proton transfer, if your nucleophile has a proton attached to it, like a water, would be a great example of that. If there's a hydrogen, and this oxygen is slightly nucleophilic because it's pulling the electrons away, creating a partial negative. So maybe I use my carbocation as a electrophile, my nucleophile, my electrophile. The nucleophile can attack. Once it attacks, it's this arrow showing it forming a new bond there. So that would be the nucleophilic attack. the proton transfer would occur afterward, because once the nucleophile attacks, it's now unstable with a positive charge. So if it lost a proton, it would balance out its charge. So another water molecule or some other base that might be around could pick that proton up, and then these electrons could stay here. So the nucleophilic attack has one arrow in this example. Proton transfer always has two arrows. This water would become H3O plus, and the rest of the structure would balance its charge and become relatively stable. So this could be one way to make this alcohol, if I can get this carbocation to form. But we'll talk about the application of these reactions in specific examples and syntheses later. So that's just one example. I'll check out your quiz answers and see if I can give you feedback if you have issues or problems with yours. If I want to do a loss of a leaving group followed by a carbocation rearrangement, that's a pretty common thing. So I might have some carbon chain, I might have a leaving group attached here. We don't need to worry about the identity of that yet. If this leaving group were to leave, by definition, it has to leave with the electrons. So it would create a carbocation. This particular example doesn't quite meet the question that's asked, because this secondary carbocation that's bonded to two carbons wouldn't have any reason to rearrange. So maybe if I put another methyl group here or a couple methyl groups here, now I can answer this question, because once a leaving group leaves and creates a secondary carbocation, the neighboring atom here has a methyl group that could shift over one more atom, and so that would create this. Right now I've got 4 bonds on this carbon here. Once a methyl group shifts over and now is located here, now I've only got 3 bonds, so my carbocation moves. So I go from the less stable secondary carbocation to the carbocation that's tertiary and stabilized by hyperconjugation more effectively. So that's just another example. Again, I'll give you more feedback on your examples. So those are a couple examples of combining some of the patterns we saw. We'll see a couple more examples of combining patterns. So here's a reaction where I want to get rid of this OH group and put a bromine on. And so here I've got a few things occurring. What's the first thing happening here? Well, this lone pair is picking up a proton from an acid. So this first step is proton transfer. 2 arrows, the base picks up the proton, the acid keeps the electrons behind that it was sharing with the proton. And that produces the structure here. Right now the oxygen is protonated, it's got a positive charge. Part of the reason I'm adding the HBr is so that the Br minus will be present to come in and connect here. Another reason I'm adding the HBr is because it's a very strong acid. Its pKa is probably around -10. The pKa of this oxygen here is probably around 0. So there's a pretty big difference between those pKa values. That means this first step is going to really shift toward the product side. And when it does, this oxygen becomes a good leaving group. So if the oxygen were to leave first, it would create a negative charge on the oxygen. That's pretty unstable. So by adding the acid, I'm converting this weak or poor leaving group into a much better leaving group. Now that the oxygen's positive, because it picked up the proton, it really is strongly pulling these electrons. So even a weak collision could have enough energy for the oxygen to pull those electrons away and balance its charge and create a water molecule. If the electrons get pulled away, this is a loss of a leaving group. In this case, the leaving group is a water molecule. The water molecule leaves with the electrons, becomes H2O, and that leaves behind a carbocation on that site. And similar to the example we just looked at, since that's a secondary carbocation, only stabilized by hyperconjugation with 2 carbon groups, if a methyl were to shift over in a carbocation rearrangement, I would create a tertiary carbocation that would be more stable, and that would happen before the Br minus comes in. Because if the Br minus were to come in here, it would not happen very often. Right? From kinetics, we learned a collision is required to break or form bonds. So if I want to form a bond between this bromine's lone pair and this carbon, it requires a collision specifically where the bromine collides at that carbon. And that may not happen very often. Comparatively, if this structure just collides with the wall or a solvent molecule or any type of collision it undergoes, that collision probably will very quickly allow a methyl group to shift over there and create the more stable carbocation. So because that's intramolecular, it doesn't require two different structures to collide, it only requires one structure to collide with anything. It's going to be, that type of collision is going to occur more often, and I'm going to get the rearrangement for most of the molecules. There may be a few of these molecules where the bromine collides directly here, but most of them will rearrange to produce a more stable carbocation. Then that will persist in reaction until the Br minus collides there, and that gives me my product. And so that last step is a nucleophilic attack. Right, the nucleophile starts to share its electrons with the electrophile to make a new sigma bond in a nucleophilic attack. So this is a mechanism that involves each of the four patterns going from an alcohol to an alkyl halide. Sometimes a reaction might involve more than one pattern occurring at the same time. So here, what am I seeing? I'm seeing this lone pair starting to be shared with a carbon. What is that? That's a nucleophilic attack. Right, this is my nucleophile. It's attacking and sharing its electrons with the carbon. At the same time, I have a loss of a leaving group. I can't do the nucleophilic attack first because this is a 4-bonded carbon. I can't make a fifth bond unless one of the old bonds breaks. And I can't do the loss of a leaving group first because if the leaving group were to leave first, before the nucleophile collides, they create a primary carbocation, which, as we said, has very little hyperconjugation and is not very stabilized when there's no resonance or anything to stabilize. So primary carbocations typically are too unstable to form in most reactions. So this reaction requires both to occur at the same time. The nucleophilic attack has to happen in just the right orientation, which we'll talk about more later, as the leaving group's leaving. Those two have to happen at the same time in order for it to go through a relatively stable pathway. And there are hundreds of different mechanisms that involve these four main patterns: nucleophilic attack, loss of a leaving group, proton transfer, and carbocation rearrangement. So part of this skill that you need to learn here involves also recognizing when arrows are not reasonable or they're not showing correct movement of electrons. So make sure you follow these key rules and avoid some of the incorrect things that we're going to show as well. So as we said, an electron pair or an arrow shows electron movement. So it always has to start on a pair of electrons. What? Either it starts on a lone pair or it starts on a bond pair. Here this arrow is showing a new bond forming. Here this arrow is showing the bond breaking and the loss of the leaving group, keeping those electrons, taking them with it. This isn't good. One of the problems here is I need to show the lone pair. If I don't show this lone pair, it looks like the arrow is starting on the atom. The arrow must start on electrons. So I've got to show at least one of the three lone pairs here so I can have the arrow starting on a pair of electrons. Same thing here. This arrow is starting on a carbon. Never start an arrow on a carbon unless that carbon has a lone pair and it's going to use to attack something with. So if the carbon has 4 bonds, the carbon itself doesn't have any electrons. I can't start my arrow there. It should be starting on a pair of electrons. It's the electrons that the chlorine's taking with it. The carbon is not moving. So make sure you start your loss of a leaving group pattern curved arrows on the bond that's breaking and going with the leaving group. The arrow starts on a pair of electrons, the arrow ends on a nucleus, or in the space between two nuclei. So if those electrons are going to end up as a lone pair, the arrow points to the atom that lone pair is going to exist on. If the electrons are going to exist as a bonded pair, then the arrow points to the atom where that bond is forming. If I were doing something like this, let's say I had a carbocation here, and I want these electrons here to end up shared as a double bond between these carbons so the carbocation can complete its noble gas configuration. Right now this carbon here, call these 1, 2, just keep them straight, 1, 2. Carbon 2 has only 3 bonds, so it's really unstable. Here it's got 4, that's better, more stable. Carbon 1 looks fine to begin with, but in order to form this product, carbon 1 has to lose one of these hydrogens. So this would be a situation where I would have to do a proton transfer. My base would pick up this proton, and these electrons would swing in here to form the double bond. Right, so as far as the rules governing the arrows goes, this arrow is good. It starts on a pair of electrons. It points to the atom where it's going to be forming a new bond. So that base is going to end up sharing electrons with that proton it picks up. This arrow is good. It starts on the pair of electrons that's moving and ends up pointing to the space between these carbons where that pair of electrons ends up. Right, so for this arrow here, don't just show it ending up on the carbon because it doesn't end up as a lone pair on that carbon. Show the arrow ending in the space between the carbons because that's where those electrons end up bonded between those carbons. So there's a lot of subtlety here and a lot of nuance, and I'm going to get real picky with your arrows. So please practice and make sure your arrows are going the right place. If your arrow isn't quite pointing in the right direction or it doesn't start on the right spot, then you're going to be missing a lot of half points here and there. So try to practice that and be as careful as you can. So make sure you start the arrow on electrons and end the arrow on atoms or space between atoms. Third rule, avoid breaking the octet for second energy level atoms. Right? These elements can never have more than 8 electrons. So just make sure you don't draw an arrow that would indicate that the atom would start to have more than 8 electrons. Right? If I just drew this arrow, and that was the only arrow I drew, so if I was saying, hey, draw the arrows for this reaction, and you just drew that arrow, what you'd be implying is happening is that the oxygen's forming a new bond to that carbon, but if that's the only arrow you draw, you're indicating that that carbon still has the other things bonded to it, which is not possible. And as I was saying earlier, draw in these hydrogens. A lot of times people don't draw them in, and that's fine because that's the bond line structure. You don't have to draw them in the bond line structure. But if you don't draw them in and you just say, okay, this oxygen is going to bond here, and you expect that to be okay because that new bond doesn't look like it creates a 5-bonded carbon, you're overlooking, obviously, the fact that you are making a 5-bonded carbon, that's really unstable. Because those hydrogens are there, if you don't draw them, you might not realize that you've made a massive mistake. So make sure that if you are drawing arrows, that you don't create any 5-bonded carbons, or really any instance where you have more than 8 electrons around any one of these second energy level atoms. And so that's why in this case, if we want to avoid that, we need to show as the nucleophile is attacking, the leaving group leaves at the same time. And then in general, try to stick with the 4 key patterns: the nucleophilic attack, loss of a leaving group, proton transfer, carbocation rearrangement. Try to avoid anything that doesn't fall into one of those patterns. So, this is good. I've got a nucleophile attacking. I've got a loss of a leaving group. I'm producing reasonable products. I'm not breaking any of the octets for the second energy level atoms. My arrows both start on pairs of electrons. They both end on atoms where the electrons end up existing. That's all good. But down here I've got obviously a problem. I'm not just going to like randomly move electrons across the molecule, right? That doesn't match with any of the four patterns, and it's not a reasonable way to show electron movement. All right, so I might give you an example like this where I expect you to fill in the arrows. This is something you should practice. So if I'm asking you to fill in the arrows, you want to look at the reactants, and you want to look at the product, and imagine how the electrons would have to shift to get from one state to the next. So what's the difference here? And this is where it's really helpful to draw in the hydrogens anywhere where there's a change occurring. And so if there's no change occurring over here, I don't need to worry about drawing in the hydrogens there or here. And this is an instance where drawing in the hydrogens isn't that important. But if there is any change, if there were any bonds breaking or forming on any of these carbons where there are hydrogens, I would want to draw them in to make sure I don't make any major errors. So what's happening here? What I'm seeing is I'm forming this new bond. That wasn't there before. And this pi bond is breaking. That wasn't there. I mean, that's not there in the end. So I look for the changes that are occurring and then use my arrows to communicate those changes. Right? So what's happening here? This oxygen had 2 lone pairs. It ended up with 3. So there's an extra lone pair. Where was that? Well, it must have been this pair of electrons here. So I'm just going to move this bond onto the oxygen to show it becoming a lone pair. And I'm forming this new bond here. So how can I show that? Well, I'm just going to show the nucleophile, right? This oxygen has 2 lone pairs. It did start with 3. So one of these 3 is going to do a nucleophilic attack on that carbon to form that new bond. So that would be a nucleophilic attack. So now I want to look at what are the arrows that are going to allow me to get from here to here. So what's happening there? Well, when I compare this structure here, this intermediate, with what I'm going to form next, I see I don't have 3 lone pairs anymore, and I've reformed the pi bond. So I'm just going to move this back in to reform that pi bond. I can't only do that though, or it would create a 5-bonded carbon. I can't make a double bond there and still have 3 bonds. And since I see this group is now on its own with a negative and 3 lone pairs instead of 2, that tells me that this is my leaving group. Loss of a leaving group there puts a 3rd lone pair on that oxygen. So I've got the 2 arrows for the first 2 steps. The first step is a nucleophilic attack. The second step is loss of a leaving group. And then what's happening down here? These electrons end up picking up that proton. It's not there anymore. And so I'm just looking at the differences between the reactants and the products. I see the proton's not here. It's over here. How did it get there? The electrons have to pick it up to form the new bond, the new OH bond. But I also need to show the second arrow associated with any proton transfer. This pair of electrons will stay here as a lone pair on that atom. Right, so that means you may have to draw in the lone pairs, or you may have to draw in hydrogens to be able to see the differences between the reactants and products, and then use the arrows to communicate how the electrons move to get from one step to another. I might ask you to identify unreasonable arrows, like in the other quiz question that we're about to talk about. So let's look at these careless arrows I made. What's wrong with this first arrow? Well, the main problem with it is it starts on the carbon. So that's no good. What's happening here? This pi bond here is becoming a lone pair. So the arrow should start on the pi bond and point to the oxygen. So it seems like it's not a big difference, but it really hurts my feelings when you start the arrow on the atom. So start on the electrons and show how those electrons are moving. What's up with this arrow? Well, this arrow would be indicating that this oxygen is forming a sigma bond with this carbon, but that's not what's happening. It's not there. So this arrow is not correct. What's happening here? Here's an example where drawing in the hydrogens is really critical if you don't see where they are from experience. Right? There's only one hydrogen here. There's two here. So to get from A to B, I've got to remove one of those hydrogens. And I've got to form the pi bond. So since this pi bond is moving up to form the third lone pair, it must be one of these hydrogens that's shifting a pair of electrons in to make that pi bond. And so that means the oxygen should be picking up that proton. So I go from 2 to 1 proton connected there. So this is a proton transfer. Proton transfer step. We fix the arrows. Okay, let's look down here. How do we fix these arrows? This is a common mistake that students make. To show the loss of a leaving group, they put the arrow on the atom and then say the atom is leaving. And that's not terrible, but it's not correct because we're using the arrows to show electron movement. So it's not, we don't want to start the arrow on the atom because that doesn't really tell us what's happening with these electrons. We want to be clear, these electrons are leaving with the leaving group. So this is not the correct answer or arrow. We want to put our arrow on the electrons and have them leave with the leaving group, which would leave behind the carbocation. When you do a carbocation rearrangement, it's common and incorrect to show the positive charge moving. Again, the arrows are not meant to show nuclei or positive charges moving. They're meant to show electrons moving. So even though the positive charge does end up on the next carbon, it's not like the positive charge is moving over. What has to happen is a hydrogen there, which no longer exists, is moving with its electrons over to that carbon. So a carbocation rearrangement requires you to show a hydrogen or a methyl group shifting over, whichever is the case. There's only one hydrogen here. In the end, there's two. So drawing in the hydrogens really helps to see this hydrogen needs to move with its electrons over to that carbon. Here in this last step on the slide, I want to make this pi bond. Where are the electrons coming from for this pi bond? It's hard to see until I draw in the hydrogens. There's one hydrogen here. There were two at that carbon. So that tells me one of these hydrogens is going bye-bye and its electrons are moving in to make the pi bond. Right? So this bond doesn't make any sense. This would imply that the oxygen is going to bond to that carbon. Well, it's clearly not there, so that's not happening. This arrow would imply that the CC sigma bond is moving in to make that pi bond. Well, that can't happen. That'd make a 5-bonded carbon here. And what would happen to this carbon if these electrons leave it? It would be on its own as a carbocation. That'd be really unstable. So this arrow you can't push electrons in to make a pi bond if one of those carbons involved becomes a 5-bonded carbon. It's too unstable. So we need this lone pair or this sigma bond to be the one that shifts in to stabilize the carbocation, and this oxygen will have to pick up that proton. So this is another proton transfer. This one was a carbocation rearrangement. Questions about those? Alright, here were the ones from the quiz question. So if we look at this first one, showing the nucleophile attacking, that's fine, because the nucleophile does end up connected there. So this arrow shows that pair of electrons starting to become shared with the carbon. Good. Problem is, how did the leaving group get away? We got to show that. So we need another arrow here to show the electrons leaving with the leaving group, and they're going to end up there. In this example down here, if the nucleophile picks up this proton, the electrons stay behind and push out the leaving group. You could imagine that happening. That would allow the nucleophile and the hydrogen to form a bond, which we've got. This electron pair shifting in, pushing out the leaving group would cause the leaving group to be on its own, which we've got. But if this hydrogen moves its pair in here onto that carbon, it's going to be a lone pair there. And since there are 4 bonds to begin with, now the hydrogen's gone and the leaving group's gone, there are only 2 bonds and a lone pair. So this carbon does not have a complete noble gas configuration. It's very unstable. It's called a carbene. Carbenes are very unstable because the carbon doesn't have a noble gas configuration. So given how unstable that is, this is unlikely, and the fact that the question tells you you're forming this pi bond, that also means that these arrows are not correct. So what do we need to do to get this product? The hydrogens. Draw in the hydrogens in the area where there's a change occurring. So I can see this hydrogen is still there. Nothing is happening to it. There shouldn't be any arrows involved in that hydrogen because it's still there. What's happening is one of these hydrogens is gone. I'm going from 3 hydrogens on this carbon to 2. So really the nucleophile, which is actually acting as a base in this case, needs to pick up one of these 3 protons, and these electrons will shift in to make the pi bond that's pushing out the leaving group. In the last example here, this arrow is showing a methyl group shift. If I follow this arrow and move the whole methyl group over from here to here, this methyl group would now be located here, and since there's 1 hydrogen here to begin with, and it's still there, that would create a carbocation. So this arrow would get me from a secondary carbocation to another secondary carbocation, which is not any more stable than it was to begin with, so there's no reason for it to do that. The process should make the carbocation more stable. So to get there, instead of moving the methyl group, I need to shift the hydride over. So there's I want to point out a little difference here. Notice this arrow here. It shows the electrons moving to the space between the carbons. That's correct because those electrons end up shared between the carbons. This arrow shows the electrons moving all the way over to this carbon. And that's correct because those electrons are not forming a pi bond. They're shifting all the way over there to form a new sigma bond. Right? There was 1 hydrogen here. Now there are 2. So this arrow is implying that the hydrogen takes its electrons away from this carbon, moves with those electrons over here to form a new sigma bond there. And that goes from a secondary to a tertiary carbocation. So now there's more induction and, even more importantly, more hyperconjugation to stabilize the positive charge at that site than at the initial site. Any questions about any of that? Alright, so just a little bit more detail about carbocation rearrangements then. You can only shift a hydride or a methyl. Okay, so I'm not going to shift an ethyl group over. Too many atoms would have to shift at once. Right, so we don't want to do that. We only want to look at methyl groups or hydrogens on the very next carbons over. We're not looking at ethyl group shifting. We're not looking at hydrogens shifting from 2 carbons away. Only the very next carbon. Right, so if you have a carbocation, anytime you see one, before you do anything else, think about the possibility of it rearranging. Because the rearrangement is intramolecular, it's likely to happen with any collision relatively soon before anything else happens. So you want to always consider that as your first option. So when you're presented with the carbocation or one forms in a reaction, look at only the adjacent atoms, look for hydrogens, and look for methyl groups. Any one of those 4 could shift, whichever produces a more stable carbocation. Right? So if I shift either of these hydrogens over, the carbocation I form here, which is still secondary, so there'd be no reason to do that. It's not going to make it any more stable. If I shift this methyl over, same thing. If this methyl leaves, then this carbon will become secondary. It won't be stabilizing the carbocation very well. So it should be this hydrogen here. That will leave the carbocation here, which is at a tertiary site now, which is going to be much more stable for it. And so that's what this is showing here. If the hydride shifts, it creates a more stable, goes from secondary to tertiary. I also always want to consider the possibility of resonance. If resonance could stabilize the carbocation, I want to do a shift that will allow that to happen before I'm worried about secondary versus tertiary. And so this example here illustrates that. Here I've already got a tertiary carbocation. So you might say, well, if it's already tertiary, why would it rearrange? Well, it would rearrange if it can become more stable. So I want to look at all the adjacent atoms. These hydrogens are not going to shift. If any one of these 6 hydrogens were to shift over, the carbocation would be left on a primary site. That would be really unstable because there's no resonance to stabilize it. I could shift over this methyl group. There's a hydrogen here I could shift over. So which makes more sense, to shift the methyl or the hydrogen? Well, if the methyl shifted, I would get a secondary carbocation stabilized by resonance because it would be allylic. Secondary, still not as stable as tertiary though, so it's the hydride that I want to shift over here. If I shift the hydride over, that hydrogen will now be here on what was the carbocation, which is no longer a carbocation because now it has 4 bonds. When the hydrogen moves, it won't be here anymore, and so now this carbon will only have 3 bonds. So that's my carbocation. It rearranged 1 carbon over, and now it's in an ideal position. It's on a tertiary carbon. This pi electrons are close enough because it's allylic. This pi electron pair could shift over here through resonance. That would create an alternative resonance contributor that would also have a tertiary carbocation. So I've got 2 individual contributors that look pretty decent because the carbocation is not terribly unstable on either of them, which means that the resonance hybrid, where the positive is shared between these 2 atoms, since the positive exists on both of them in individual contributors, the hybrid that would have half a positive on each of these locations would be pretty stable comparatively, and that would be the most likely rearrangement to produce the most stable carbocation that I can make before something else happens like a nucleophilic attack. Alright, this next section I'm going to kind of go through quickly because I don't expect you to necessarily be able to judge yet which side of a reaction is more stable. We talked about this to an extent. Obviously it's at 2:50, so if anyone needs to go, you can come back and check out the video later if you have something going on at 3, obviously. Just want to point out, sometimes when a reaction occurs, it's considered reversible, and that would be because the reactant and the product are similar in stability. How similar do they have to be? And that's the problem with this section. I don't expect you to have the experience yet to be able to really judge what side of a reaction is more stable than another side. We did talk about scario, so we have some ability to judge when a negative charge is stable. So if this negative charge stabilized through resonance, probably a little bit more stable than a negative that's not. But this one's on an oxygen, and this one's shared between an oxygen and a carbon, so that's pretty similar. So these 2 negatives look pretty similar, which is why the equilibrium would probably produce some reactants and some products. The next step here, though, where I've got the negative on a carbon and oxygen shared through resonance versus only on a bromine, well, this is way more stable. The larger the atom, the more it stabilizes the charge, and since the atom comes so early in that acronym, it's a big factor, and that's why this second step wouldn't go backwards. I'm not going to see the bromine pick off this proton and reproduce HBr. It's not going to be a stable situation. Oh, that's not the reverse. The reverse would be if the bromine picks up this methyl group and these electrons stay behind. Either way, creating a negative on a carbon compared to a negative on a bromine. It's not really much of a contest, so that reaction is not significantly going to go backwards. Whether or not something is reversible is both a kinetic and thermodynamic question, and that involves a lot of detail. So we'll talk about that later in the context of some specific examples. So let's imagine quickly a nucleophilic attack. The nucleophile attacks, if we create this structure here, is that reversible? Sure. I mean, I don't expect you to know that yet, but through the examples we'll talk about over time, you'll develop that skill. So here I've got instability on this carbon because it doesn't have a complete noble gas configuration. Here I've got instability on this oxygen because it's such a highly electronegative atom, and it's starting to rip away these electrons due to its electronegativity, and the fact that it's positive, it means it attracts the electrons even more. So this water could easily leave and go back to form the carbocation, or it could come back in and reform the bond. So that's a reversible process that can go in both directions because both sides are similar in stability. And that's what we're talking about here. What about this one? Well, in this case, with a negative on a carbon, that's really unstable. The charge imbalance there is pretty unbearable for the carbon. So if it comes in here and attacks, a nucleophilic attack pushing these electrons up, and now I've got the negative on an oxygen, that's not very likely to swing back in and push that carbon out, because a negative on an oxygen is way more stable than a negative on a carbon, right? We talked about the atom carrying a charge makes a big effect on the stability of that charge. So oxygen versus carbon is a pretty big difference. And that means that once the negative forms on the oxygen, it's not going to go back to the carbon in any significant amount. We can, technically it is reversible, like everything's technically reversible, but the degree to which it goes back is virtually negligible. Loss of this leaving group. So if that leaving group loses, I get a carbocation and a Br minus. Is that reasonable? Well, Br minus is really stable as a negative, but this carbocation is really unstable because of the charge and the incomplete noble gas configuration. So that nucleophilic attack to go back would really favor the reactant side. So in this case, this is so non-spontaneous that the reactant would be like percent. The amount of carbocation existing in solution at any moment isn't completely zero, so technically I'm in a form of some degree of an equilibrium, but it's almost nothing because it's so much more unstable than the original structure. So again, it's hard to know that, which is why we're talking about this, so you can get some experience. If you're talking about the reversibility of a proton transfer, you can use pKa values. Right? So we know from chapter 3 that if I've got an acid reacting with a base and I look at the other side and I have the conjugate acid that the base turns into once it picks up a proton, if I have the pKa values of the respective acids on either side, I know the equilibrium is going to favor the side with the higher pKa, and I know the difference in the pKa units is going to be a factor of 10. So 16 about here, this is about 16 roughly, versus 50. So that's like 10 to the 34th power more products than reactants. So technically I have some reactants, but the amount is virtually nothing because the equilibrium so greatly favors the product side. In comparison, if my pKa values are only a few units difference, well then I still have at least something on each side. So here I still have about 100 times more products because they have a higher pKa and it's a little bit more stable than the reactants, but I still have a significant amount of reactants. So even 1% is still significant. This value is so large, I've got way more products than reactants. The reverse reaction really is not significant, right? So that's the difference there. We don't usually think of carbocations as reversible, and that's because once the carbocation rearrangement occurs and I go from secondary to tertiary, or from not stabilized by resonance to maybe one that's stabilized by resonance. So if I had this situation here, this proton could shift over to give me a resonance stabilized carbocation. We don't really think of those as reversible. Technically they are, but again, the degree to which the more stable, and the fact that that can shift very quickly means it's going to reach equilibrium very fast. Since it's intramolecular, it happens very quickly, and so almost all the molecules will be in the more stable carbocation form. There's enough of a difference between the stability of one carbocation and another that usually happens quickly and in a, for all intents and purposes, irreversible way. Sometimes Le Chatelier's principle can tell you that a reaction is irreversible. So in this case, having a negative on a nitrogen is much more stable than a carbon. So you might say, well, this carbon should be able to come back in here, attack like a nucleophile, push these electrons up here, and recreate the negative on the nitrogen, reform the sigma bond between the carbon and the nitrogen, and go back. The problem here is that this is a gas, and as soon as it forms, it starts to bubble out of the reaction. So how can the carbon collide with it and reform the reverse of reaction if it's leaving? It might happen once in a while, but by Le Chatelier's principle, if every time this gas forms, a little bit of it bubbles out and it can't come back in, eventually that's going to cause the reaction to completely shift toward the product side. So this is a nice way we can actually take advantage of this to make something that normally would be unreactive compared to the product, and we can force it to produce something that's even less stable, because the reverse reaction can't happen if one of my reactants evaporates out as a gas. So we can use Le Chatelier's principle to drive this reaction to produce something that's really unstable that we can then use to do another reaction and start to make like a new carbon-carbon bond or something like that. So we'll see more examples of that moving forward as well. Any questions about anything from today? All right, well, there's lots of practice for y'all to do. Heads up about Thursday. Thursday is a review day. So mostly because these curved arrows are like a new language you're kind of learning. It takes a little while to establish that foundation in your learning, and it's really important before we move forward that you do that. So try to practice as much as you can from chapter 6 before Thursday. Send me any questions you have about anything. We can talk about lab stuff. We can talk about any of the quiz questions that we've done previously, examples from the textbook. If we run out of questions that you have, I will prepare some questions. I'll make up some questions that'll be my effort to help you prepare for your exams that are coming up starting on next Tuesday, next week. So next week's exam is, I'm pretty sure it's just going to be focused on this day 13 stuff. So we can do a lot of practice around that, and having a day off from lecture will hopefully allow you to catch up a little bit on lab stuff as well. And so that's the plan. These videos and chapter 7 are for you to prepare for next Tuesday, which is day 15 on the syllabus.